about transitive waves and in kagome superconductors whenever you're ready.
Thank you. So my name is Eduardo Bittar. I'm from the Brazilian Center of Physical Research in Rio de Janeiro. I thank the organizers for the invitation to show my work. And I'll be talking mostly of charge density waves. And as most of you know, it's a modulation of the conduction electron that's accompanied by a distortion of the lattice. For the one-dimensional case, there is a theoretical solution for it, but for most real materials like 2D or 3D, there's no theoretical description for the charge density wave, at least not an exact solution. So from an experimental point of view, what is the signature of this charge density wave? And for 2D materials, one can see an upturn in electroresistivity, that it's the partial opening of the charge density wave gap at the Fermi surface, okay? But for 3D materials, this upturn is not as clear as in 2D, and it goes a little bit like up here in this lutetium platinum indium compound, okay? It also decreases the magnetic susceptibility because there is this partial opening of the gap of at the Fermi surface. We also can see in STM measurements, okay, then you can see the real orientation of the new orientation inside the superstructure, and also by X-ray and Newton diffraction, where one can observe extra peak, a diffraction peak, where from the temperature that the charge density wave sets in. Okay. So some years ago, there was this work on this 3D material that it's calcium, strontium, iridium, and tin, and they doped and applied pressure, and they looked at the electroresistivity as a function of temperature and pressure for different pressures, and they see the suppression of this kink in the electroresistivity, and they assign this as the suppression of the charge density wave, and also from the behavior of the electroresistivity from a Fermi liquid to linear behavior, they assume there is a quantum phase transition, a quantum critical point, once the charge density wave is suppressed. So a few years later, another work on this lutetium platinum indium doped with palladium, they also see the suppression of the charge density wave and the enhancement of the superconductivity. And here from some thermodynamic properties such as specific heat and electroresistivity, they assume that it's also a quantum critical point. Okay, so in both cases, the enhancement of superconductivity would be due to the suppression and quantum fluctuations. Okay, so this it seems plausible, but it also has this issue because once you suppress the charge density wave, the density of states at the Fermi level is increased, and you also can increase your TC just because you're closing the gap and promoting more electrons to the density of states at the Fermi level, and then you have a higher TC. Okay, so it could be something as simple as that. So we looked a few years ago into these questions, and we measured the diffraction pattern, X-ray diffraction pattern for both systems, okay? This one was under pressure, and this one was by palladium doping, and we mapped the intensity of the superstructure peak as a function of temperature for the different samples. Okay. And one can correlate the intensity of the charge density wave its temperature dependence with the order parameter exponent, critical exponent. Okay, so we mapped that, and then we saw that as the system approaches the critical pressure or the critical doping for the charge density wave, the behavior of the critical exponent changes also. So this is an indication that the system moves from this university class to the mean field value, indicating that it reaches the upper critical dimension. Okay, so the system, the critical exponent of the order parameter changes from 0.3 to 0.5. That it's the mean field that expected for the mean field value. So this is some indication that both systems are actually have some quantum fluctuations, indicating that it might be a quantum critical point. And this has been seen in a lot of systems over the years. So this is well known in the cuprates and also in many intermetallic compounds ranging from 2D to 3D, and now these nickel oxide materials, these new oxide materials, where you also see a density wave order and then suppress and have the superconductivity. Okay, but the question is still open if this charge density wave competes or coexists or cooperate, or is just something independent to the superconductivity. So we've been looking at some materials over the years, and we look at this 3D material that is 3413 with earth, transition metal, and tin. And recently we looked at this lanthanum cobalt tin compound, and we mapped the superconductivity state under uniaxial pressure, okay, and we see some difference on the way that TC is suppressed in different crystal orientations, and from this that is submitted to PRB, we can infer something about the superconductivity gap, okay. We also looked at this calcium rhodium tin compound, okay. This work was done in collaboration with Los Alamos, and this one was done with collaboration with the people at APS. In this compound, we looked at the charge density wave with X-ray, dark field X-ray microscopy, okay? And we looked at the charge density wave in real space, sorry, Dominus, and what we see, so this we are still analyzing, there's a lot of data and we are learning how to process, but it seems that the domains of the charge density wave changes once it goes into the superconducting state. So this is something that you should get out soon, okay? Another system that we're looking, it's the scandium vanadium 610-6. This one is a charge density wave system. It doesn't have superconductivity, but changing tweaking something in the heat treatment of growing these crystals, we could grow along the C-axis, since these type of kagome metals are like flat crystals. Okay, so we grew this along the C direction and looked as a function of strain, and we see some differences in the C-axis and the A-axis, and it's also a little bit different from the hydrostatic pressure results. So now, getting into the main theme of the talk. So we are looking at this kagome AV3 antimonium 5. So a lot of people already talked about it in the previous talks, and I thank people for that, so I won't take much long here. But the thing is that you have this compounds that they have a lot of different ground states or different properties that one have been seen since its discovery. Okay, there's the pure cesium compound and the pure rubidium compound, and they can be they present a charge density state order and superconductivity. Okay, as you pressurize it, one can suppress the CDW and enhance superconductivity. The same is for doping. Okay, the same can be seen for doping. And also, one can do some isovalent doping, changing the cesium for rubidium and potassium, okay? And then you go from one parent compound to another, like changing slowly the property, the order temperature for the CDW and TC, okay? So we thought, okay, let's take a look at these kind of systems that have not been reported. There is this report, but just that it's some microscopic properties. So we grew the samples of this system here, okay? And this work was done in collaboration with the Synchrotron Lab, USP, and San Diego University, but it's like a local collaboration because Milton is Brazilian and all his research, all the data that he worked was done here in São Paulo, where he was a visiting professor. Okay, so all the work here was done in Rio and São Paulo, and I'll just tell you that this is a work in progress, so we don't have any conclusions, but since this is a workshop, I thought it was nice to bring you guys our preliminary results. So we did some microscopic characterization of our samples. We have the pure compounds and one with 10, 30, and 50% of rubidium doping, okay? And summarizing, what we see is an increase, like a monotonic increase of the charge density wave and a monotonic decrease of the superconducting temperature, okay? And we looked at the crystal structure, okay? And what we see is that the C parameter of the unit cell decreases as a function of rubidium doping, okay? As this temperature which the CDW sets in increases, okay? And this is it's different from what was observed for the pure compound, for the pure cesium compound under pressure, that the C lattice parameter decreases and also decreases the charge density wave, okay? So this is something that we are now trying to understand, and of course look again at the data to see if everything is correct. But we have these different conflicting results. We also applied pressure to the 10% doped compound, and what we see, it's a very similar trend as the pure compound, the pure serum, so the TC goes up and down again and up, and the charge density wave just is suppressed. We looked for the 50%. It also looks quite similar at here for the potassium and rubidium side. Okay, so TCW decreases and superconductivity is enhanced. And we also looked this for the highest pressure that we attain for the 0.1 compound and for the 0.5 also, but I just show here for the 10% doping, we see an increase of the critical field for the superconducting state. So it goes from around 0.7 to 7. So we see and 1 order of magnitude increase. And we saw this morning that this might be an indication of a new state, okay? But it might be also something with the doping, and this is something that we're looking. But anyhow, we see an increase of 1 order of magnitude of the critical field with doping and pressure. And also the pressure is quite small, okay? But this is something that we have to look at, but it might be an indication of a different type of superconductivity of the ambient pressure superconducting state, okay? So, we also did some strain, uniaxial strain measurements, and this is something that we just started. Here we see the derivative of the magnetic susceptibility. So we measured the magnetic susceptibility in the uniaxial strain cell. And from the derivative, we can see 2 peaks, probably because the sample has some, it's not homogeneous, and we'll have to look at that. But if you map the both peak, we have a linear behavior of Tc as a function of the strain, okay? And this has been seen for the pure cesium compound, okay? But here we have a 16% decrease instead of 18. And we have to look if this is something that it's, why this happens. We also wanted to get some information about the local structure of our materials, and one way to do that is to look at the XF spectrum. So the XF spectrum is generated by the absorption of X-rays in the K edge of the material, okay? And from the absorption, you have these 2 regions, the xanes, which is near the edge of the absorption, and a more extended spectrum, okay, that has these wiggling features. And from that, one can extract the interatomic distance. I guess this is the important information here, that one can obtain the interatomic distance of the absorbing atom, okay, of the local structure. So let's see. So for this, we had to go to the synchrotron lab. We use the EMA beamline, okay, that has these characteristics. So this is an information for you guys, the kind of materials and kind of physics that one can do at the synchrotron here in Brazil. So we looked at the rubidium compound, the pure rubidium compound, and the structure has 2 antimonium atoms, one in the plane and one out of plane. The rubidium and they are out of plane, and the vanadium are also in plane with the the antimonium 1 atoms. Okay. So we looked at the Kizev's pattern, and here I will just show you the results. Okay. So for the pure compound, the rubidium compound, at ambient pressure, we see an increase of the interatomic distance between the antimonium and the rubidium, okay, at the temperature that it occurs, the charge density wave. And as we apply pressure, the temperature goes down, as the phase diagram says, and also this jump in the atomic distance between the antimonium and the rubidium changes to lower temperature. So if we go in the phase diagram as a function of pressure, we see a decrease in the temperature in which these jumps occurs. If we look at the vanadium, the antimonium 1 and the vanadium distance, there's also some change at the charge density wave transition, okay? It goes in a different direction than the rubidium, okay? So it's like it's getting closer in the plane and longer in the outer plane. Okay. So this is the main result. We also looked at the We also look at the antimonium 2 again. So I'll just go to the result. So here we see that for low pressure, there's no, for the antimonium 2 does not feel much this change in the atomic distance. It's only above roughly 1 GPa that it changes, okay? And the antimony 2 has a different behavior than the antimony 1, okay? So why did we look at the antimonium? That's because I think Jorg also said this morning that the charge density wave for this kind of materials, they are not exclusively in the vanadium atom, but it's also an hybridization of the vanadium with the antimonium, okay? So by looking at the local structure of the antimonium, we could track the charge density wave, indicating that there is actually this hybridization of the antimonium and the vanadium for the superconducting state. Okay. So faster. And so here's the summary of my talk. We grew some samples of rubidium doped in cesium samples. We see an decrease of the charge, increase of the charge density wave, and the decrease of superconductivity. This might be related to changes in the C lattice parameter, okay? It seems from the xRbxV results that we have an important role of the antimonium orbitals atom for this charge density wave state. We also see an expansion of a contraction of the in-plane antimonium, okay, and the expansion in this direction, okay, and it's the other way around for the antimonium 2, where we see expansion of regarding the vanadium and a contraction in regarding the rubidium atom, okay. And also something that we want to share, that xRbxV can be an emergent technique to study these structural changes with a CDW transition. And with that, I thank you the agencies that funded this work. Thank you.
Thank you for the nice talk. So, questions from the audience?
So Eduardo, thanks for this nice talk. So do you know why at 50% you get this non-monotonic behavior, this bump in the yeah,
Here?
So, at 50 at 0.5. So apparently the trend at 0.5 is interrupted. So TC, yeah.
Yeah, it might be. No, we're not sure exactly what's happening. But here one can see that the C lattice parameter changes also, so it might be some relation. But why that's happened, yeah, we don't know yet. Okay.
More questions? Okay, then that's not the case. Let's thank the speaker again. We have a coffee break now, right?